Welcome to Calc Chats 29. Today we're going to be talking about absolute convergence and the telescoping series and the alternating series test. First, we need to kind of discuss the difference between absolute and conditional convergence. So we know that if the absolute value of a series converges, then we say that the regular series converges absolutely. And so this has been the case for most of what we've talked about so far. We've just been dealing with AN, not necessarily the absolute value of A of n, but now we're going to start dealing with that. But basically, this is kind of what we've been dealing with, this upper part so far. We haven't really talked about absolute value of A of n. So every series that we've proved converges at this point converges absolutely. But now we're going to be talking about different types of series. And so we need this conditional convergence. And so if the absolute value of the series diverges, but the original series converges, then we say that the series converges conditionally. And so what this helps with is what we call alternating series. So alternating series are generally set up in the form, the sum from 1 to infinity of -1 to the n plus 1 times a sub n, where a sub n is kind of any series that we've been dealing with, any sequence, I guess, that we've been dealing with. So here's a great example of an alternating series, and this is called, you guessed it, the alternating harmonic. Because we have this 1 over n, that's our harmonic series, but we also have this alternating part attached to it. So the first few terms of the series, this would be -1 squared times 1 over 1 plus -1 cubed times 1 over 2 plus -1 to the 4th times 1 over 3. I'm just going to write out these first few terms. And if we simplify this, this ends up looking like 1 minus 1/2 plus 1/3, and you can kind of guess it keeps switching back and forth. And so this series, the alternating harmonic series, converges conditionally. And so this is one of the biggest differences we see with absolute versus conditional convergence. So the sum of 1 over n by itself does not converge, it diverges. But when we add that -1, that switching alternating power that makes it positive and negative, this is actually going to converge conditionally. And we're going to kind of see why this works, and we're going to use what's now called the alternating series test. So the alternating series test says that if we have this alternating series, and this is important, we need some kind of, I guess, number or function that's alternating. It's not always going to be -1 to the n plus 1, but this is more than likely the format we're going to see it in. But I have some alternating part and then some just kind of regular part that we're more familiar with. If I have this type of series, then if each u of n is positive and my terms are getting smaller and they're going to 0, then this alternating series converges. And so all three of these have to be met in order for an alternating series to converge. So looking back at the alternating harmonic, if we see this is our u sub n. And so if we look, all of our u sub n's are positive. Each u sub n is greater, is less than the one before it. So it's getting smaller, and if I take the limit as n goes to infinity of 1 over n, that's 0. So all three of these conditions are met, So this series converges, but then again, we have to take into consideration it converges conditionally because 1 over n does not converge, it diverges. So here's a great example where we're asked to determine if the series converges conditionally, absolutely, or if it diverges. So first of all, these kind of words maybe clue us in to that there might be an alternating series part of this, and it turns out, in fact, there is. And so first, we're really going to check the terms. And so what we can do is we can say, okay, are my terms all positive? And yes, they are. The terms are 1 plus 1 over 1 plus 1, square root of 2 plus 1 over 2 plus 1, square root of 3 plus 1 over 3 plus 1. So my terms are positive. They are getting smaller because my denominator's growing faster than my numerator, and the limit is going to 0. And so all three of those conditions are met, and so this converges. But does it converge absolutely? Does it converge conditionally? That's what we're going to have to use another test to find out. And so we can kind of look at this series, and I'm thinking there are really two ways to go. We can use a direct comparison or we can use a limit comparison. I'm going to choose the limit comparison, so we get some extra practice with that. But if you want to try the direct comparison, you're more than welcome to. So the series that I'm going to choose to compare this to, I'm just going to leave this as the square root of n over n. I'm not going to try to simplify that at all. So I'm going to take the limit as n approaches infinity, root n plus 1 over n plus 1 times, flip the fraction, we get n over root n. So we get the limit as n approaches infinity, n times the square root of n plus n times the square root of n plus the square root of n. So when we're going to infinity, I'm looking at this highest power. These kind of cancel out, and this ends up just going to 1. And so our original series diverges, and so we know that the absolute value diverges as well. So if I took the absolute value of this series, it would diverge, and so this series converges conditionally. The last thing we're really going to be talking about is called the telescoping series. And the reason this is called a telescoping series is because we end up with a lot of terms canceling out, and kind of, this is going to be a really bad picture, but really old telescopes kind of were almost like Russian nesting dolls, and it collapsed in on itself. And so it would just kind of look like that. This side goes in this way, this side goes in that way, and it would just collapse in on itself. So that's what's happening with this telescoping series. So the first thing I want to do really is I want to put this into partial fraction decomposition to try to get this to be a telescoping series, because I'm telling you straight up that this is, and so let's try to figure it out. So first I'm going to factor the bottom. I'm going to use partial fraction decomposition. So I'm going to say a over n plus b over n plus 1. So 1 equals a n plus 1 plus b times n. Plugging in -1 and 0, we get, so n equals -1. Let's do that one first. So I get negative b equals 1, and so b equals -1, and then n equals 0. We should get a times 1, so a equals 1. So this series looks like n equals 1 to infinity, 1 over n minus 1 over n plus 1. And if we start listing out these terms, plugging in n, we get 1 over 1 minus 1 over 1 plus 1 is 2. So that's the first term, n equals 1. n equals 2, we get 1 over 2 minus 1 over 2 plus 1 is 3, plus our third term, 1 over 3 minus 1 over 4. And this is going to keep going until we get to the very end, which just looks like 1 over n minus 1 over n plus 1. So we start to notice that negative 1/2 and 1/2 cancel out, negative 1/3 and 1/3 cancel out, negative 1/4 and 1/4 will cancel out, and we're going to keep canceling out. And the only two terms that will be left is 1 at the very beginning minus 1 over n plus 1 at the very end. So again, this telescoping series, everything is coming in on itself except for the two endpoints. And so with any telescoping series, we can actually determine the sum. And so when we're looking at the sum of a telescoping series, we take the limit as n approaches infinity of kind of the sum, whatever is left over. And so we see that this limit is actually equal to 1. And so this is actually the sum of our series. So with telescoping series, they're useful because we can find the sum, but if there is an easier way to find the convergence or divergence, we want to use that instead. The only real reason that we need to use telescoping series is if we're asked to find the sum, but if it just asks you to determine if it converges or diverges, a different series would be useful, or a different series test would be useful. So here's our first DIY problem. Determine if the series converges absolutely, conditionally, or diverges. So I'm going to go ahead, pause, write down the problem, try it by yourself. So here's my work for this particular series. So we know that the alternating series test works. It does converge, and then when we test using the limit comparison test, it diverges. So the series converges conditionally. So another DIY, this is a telescoping series. So if you feel good about telescoping series, you can go ahead and skip. But go ahead, pause, write down the problem, try it by yourself. So for this problem, first we have to do partial fraction decomposition. Once we get the partial fractions, we can use the telescoping series to find the sum, and you should get that the sum is equal to 1. So here's your ABC problem for the day. I'm going to pause it real quick, write down the answers. So take a minute, jot down the problems, try each of them, see how far you can get, and just let me know when you come into class what questions you have about these problems. So here are the answers. A, converges conditionally, B, diverges, and C, diverges as well. So this is the end of Calc Chats 29, so please make sure to jot down any questions that you have and to like and subscribe. And thank you for watching.